Chapter 4 Chemical Thermodynamics by Aklesh Sir.
Thermodynamics is concerned with the energy changes in physical and chemical transformations. In this above animation here, ice has certain energy in solid state. And when it convert into water, it absorb energy. So how much energy ice had absorbed during this physical transformation of solid ice to water? That thermodynamics explain. Similar for chemical reaction, also during conversion of reactant to product, how much energy is involved, that thermodynamics will explain. Limitation of thermodynamics. 1. Thermodynamics, however, does not tell us about the reaction rates of physical or chemical processes. That how, what is the speed of reaction, it does not explain. 2. It does not explain underlying mechanisms involved in these. That is how reaction had occur, how product is formed, or what was step involved, that all mechanism. Thermodynamics does not explain. Thus there is no information about speed and process of reaction detail. Consider a gas enclosed in a cylinder equipped with a movable piston, and it is heated as shown in diagram. Suppose we undertake study of change in volume of a gas and the amount of energy gained or released by a gas when the pressure is varied. In it, weight is less, that is, pressure is less. Therefore volume is more. And when certain mass is put on the piston, that is, there is a increase the pressure. This causes volume of gas to decrease. In this case, a gas under study is called the system. In thermodynamics, we divide everything into three parts: system, surroundings, and universe. Consider rectangular part represent universe, and circle represent system, and rest part other than system is called surrounding. First, let us understand what a system is. A system is the part of the universe which under thermodynamic investigation. For example, if gas is enclosed inside a cylinder with a piston, then the gas inside the cylinder is called the system. Now, what is surroundings? Everything outside the system is called surroundings. This includes the cylinder walls, piston, burner, tripod stand, air, our surrounding.
Types of system. 1. Open system. System which exchanges both energy and matter with the surroundings is called an open system. Consider an open cup containing hot coffee placed in a room. Coffee cools down, releasing heat, that is energy, to the surroundings, and the water vapor from coffee, that is matter, simultaneously passes into surroundings. Here both energy and matter both passes into surrounding, thus open cup of hot coffee is an open system. Two. Closed system. System which exchanges only energy but not matter with the surroundings is called enclosed system. Consider a cup containing hot coffee is covered with a saucer. Coffee cools down by giving away heat to the surroundings. The water vapor from coffee now does not pass into surroundings. Thus hot coffee closed with lid is called a closed system. 3. Isolated system. System which neither exchanges energy but nor matter with the surroundings is called an isolated system. Consider a cup containing hot coffee is covered with a saucer. Is insulated from the surroundings. Coffee does not cool down. Moreover, there is no escape of water vapor and heat into the surroundings. Thus hot coffee closed with lid and it is insulated is called an isolated system. One, extensive property. A property which depends on the amount of matter present in a system is called extensive property. Examples: mass, volume, internal energy, heat capacity, number of moles.
Of extensive property will depend upon the amount of matter. See here, in this case you see here mass. Why the mass is the extensive property? If the matter increases, here there is this 100 gram, here is 200 gram. As the matter increases, mass also increases. Okay, so if matter increases, the mass also increases. It means what? Mass is a extensive property because it is depending upon what amount of matter present in it. Say here it is has a more matter, here it has a less matter. As the matter increases, volume also increases. Therefore, volume depend upon amount of matter. If matter increases, amount of matter increases, volume also increases. In third example, heat capacity and internal energy. What is the meaning of heat capacity? Heat means how much amount of heat can that matter can hold. So in this case, here there is a matter is very less. In this case, that is 100 ml of water, so the heat capacity will be less. See here, you can see here the heat capacity is only 418, but as the matter increases, that is water quantity increases, that is 500 ml of water, so amount of heat it can absorb, it can hold is also increases. So here you can see 2090. So if the matter is less, heat capacity is less. If the matter is more, heat capacity is more. So heat capacity is a extensive property. Similarly, what is the meaning of internal energy? Internal means inside energy. If you compare both this case, here it has inside there is a large amount of energy there because number of molecules is there. Each molecule has certain amount of energy. So total energy in this case, that is 500 ml of water, is more. But in here the number of molecules is less, so number of molecules less, the amount of energy will be less, so inside energy is less, so internal energy is less in this case. So 100 ml of water has a less amount of energy and 500 ml of water has large amount of energy. Okay, last example, that is number of moles. What is the number of moles? Number of moles formula is what? Number of weight upon molar mass. So as the weight increases, number of moles also increases. So by increasing the amount of matter, the number of moles also increases. Okay, so number of moles is also an extensive property. Definition of intensive property. A property which is independent of the amount of matter in a system is called intensive property. Example of intensive property. First example is temperature. So how temperature is an intensive property? First, what is the meaning of intensity? Intensity means what? The property which independent, ion, see here, ion is there, you can remember like this, intensity ion independent. So property which is independent among the amount of matter present in the system means what? If the matter also increases, property will not change. Okay, for example, temperature. So we will take the example of temperature. First, what is the meaning of temperature? So temperature means average kinetic energy of the molecule. Okay, so means what? How fast the molecule is moving inside that substance. Okay, so if the molecule is moving very fast, you can say that the temperature is more. Okay, so take one example. If I take 100 ml of water, and inside that if I add a thermometer, okay, so thermometer is as I put the thermometer in the 100 ml of water, its temperature increases to 30 degrees Celsius. So the temperature of the water is 30 degrees Celsius. Okay, this red sphere represent the molecule of water. Here the number of molecule is very less because we are taking very less amount of water, that is 100 ml. So number of molecule is very less. There is a very few molecules are present in this 100 ml of water. Okay, so lesser the quantity. so here this molecule is moving, it has certain amount of average kinetic energy. Each molecule has certain amount of average kinetic energy. Suppose if I assume that the average kinetic energy each molecule is 10 joule. Okay, now what we will going to do, if I increase the quantity of water, suppose instead of 100 ml, if I take 2 liter of water, and inside if I add a thermometer, okay, so I am adding a thermometer inside it, okay, in the 2 liter of water. And now as soon as I add the thermometer, its temperature increases to 30 degrees Celsius. So we are taking the temperature same. We have heated the water such that both the temperature is 30 degrees Celsius. What will happen here, the number of molecules is more because the quantity we have taken is more. So instead of 100 ml we have taken 2 liter of water. The 2 liter of water means it has a large amount of matter. Okay, so this has many molecules present in this 2 liter of water. So this molecule is moving now. Okay, so here each molecule have a same amount of average kinetic energy. Since the temperature is same, since here also 30 degrees Celsius, here also, since the 30 degree is same, each molecule will have the same amount of kinetic energy. Okay, that is 10 joule. Okay, so even the water quantity is different. Okay, one is less amount of water, one is more amount of water, but the average kinetic energy is same. If the average kinetic energy is same, means what? Temperature does not depend upon the quantity. Means what? Since the number of each molecule have same amount of average kinetic energy, means temperature is same. Even the quantity is increased, but the temperature remains constant. So you can say that temperature is an intensive property. Okay, we will take the next example, boiling point. Okay, so here you can see we have taken 100 ml of water and we are heating it. Okay, you know that water boiling point is 100 degrees Celsius. So we are heating till it reaches the boiling point, that is 100 degrees Celsius, and it started boiling. Now what we will going to do, we will increase the matter. Okay, so instead of 100 ml we are taking 500 ml. You know, here also, even if the matter increases, it will going to boil at the same temperature, that is 100 degrees Celsius. So boiling point in both the cases same. So here you can see that the property, that is boiling point, has not changed even if the matter is changed. So different amount but have same boiling point. Boiling point does not depend upon the amount of matter. Even the matter has increased, boiling point has not changed, same, that is 100 degrees Celsius. So you can say that boiling point is an intensive property. Next example property, that is melting point. Here also you can see we have taken the lead. Here we have taken, in first case we have taken 50 grams of lead, and in another case we have taken 200 gram of lead. Even the masses are different. Okay, even the masses are different, but both will going to melt at the same temperature, that is 328 degrees Celsius. So even the matter has increased, but the melting point has not changed. They are melting at the same temperature, that is 328 degrees Celsius. So you can say that melting point is also an intensive property. Next example, pressure. Here you can see we have taken one big container, and in big container we have added a water. Okay, so here the amount of water is more, so the atmospheric pressure which is applying on this surface of the water molecule is what? 1 atmosphere. You know that atmospheric pressure is 1 atmosphere. So that atmospheric pressure is applied on the surface of the water. So here the atmospheric pressure on the surface of the water is 1 atmosphere. So pressure is 1 atmosphere. Now what we have done, we have taken very small amount of water in two different container. If here also above the surface of the water, here also that pressure is 1 atmosphere, here also the pressure is 1 atmosphere. Even if the amount is half of this, then also the pressure is same. So pressure does not depend upon the amount of matter. If amount of matter, even if it's changed, pressure will not change. So you can say that pressure does not depend upon what? Amount of matter. Okay, pressure will remain same. Therefore you can say pressure is a intensive property. Next example, surface tension. So what is the meaning of surface tension? Surface tension means it depends on the nature of liquid. Okay, so it depend upon the nature. If a liquid is not changed, surface tension will not change. Okay, a surface tension is the surface phenomena. So we will take one example, that is 50 ml of water. In 50 ml of water, you can see on the surface quantity we have taken very less. So here on the surface there is a formation of water droplets. Water droplets is a surface tension phenomena. So if the surface tension is there, the water droplet will form. Because water droplet is only when formed when there is a surface tension. So now what we will going to do here, this droplet is formed. Now we will increase the amount of water. Okay, so we have, in this second case we are taking 200 ml of water. Okay, more amount of matter we have taken here, some water quantity is more. So then also here you can see here there is a formation of droplet. So even the quantity has changed, even the matter has changed, the droplet formation in both the case you can see here, means that there is a no change in the surface tension. The surface tension produces droplets, and even the area has increased, the surface tension has not changed. So you can say that surface tension does not depend upon the quantity of liquid. Even the quantity of liquid is increased, surface tension will not change. Therefore you can say surface tension is also an intensive property. It does not depend upon the amount of matter present in the system. Next example, viscosity. Viscosity, what is the meaning of viscosity? Viscosity means what? What is the friction inside the liquid the molecule is facing? If there is inside the liquid, if the molecule are facing a large amount of friction, the viscosity will be more. If there is a less friction inside the liquid, then the viscosity will be less. So here you can see here the honey viscosity is more as compared to water. Water will flow very fast, but in honey it will flow very slow because the viscosity is more. Means what? Internal friction is more. So if I take a very small quantity of honey, that is 50 ml of water, 50 ml of honey, if I stir this honey, so I will face certain resistance. Okay, there will be a certain viscosity. If I take a larger quantity also, okay, that is 250 ml, here also if I stir it, I will face certain friction, that is viscosity. In both the case, if the stirring it has the same stirring, okay, that means if we are facing the same friction in both the case, even the quantity is more, viscosity is in both the cases same. So if viscosity is same, even the matter is changed, it means viscosity is doesn't change even if the quantity is changed. It means viscosity is also an one type of intensive property. Okay, next example, specific heat. What is the meaning of specific heat? First we will know the definition of specific heat. Specific heat is the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. What is the meaning of this? Suppose if I take a small amount of copper and the mass of that copper is 100 gram, but specific heat depend upon what, how much specific, to calculate a specific heat we require only 1 gram of that substance. So 1 gram of substance if you required, so what you have to do is we have to take 1 gram of copper from the 100 gram of copper. Okay, now we have taken 1 gram of copper here. Now what we will going to do, we will heat it, because we have to heat that 1 gram, we have to heat that substance, that 1 gram of substance, till it increases the temperature by 1 degree Celsius. So I will heat till 1 degree Celsius. So to increase that 1 degree Celsius, how much amount of heat we are required? So that amount of heat required by that 1 gram of copper to raise the temperature to 1 degree Celsius, that amount of heat is known as specific heat, and that quantity, that amount value is 0.39 joule per gram degree Celsius. So this is the specific heat of that copper. Now if I take the larger amount, that is 200 gram, then also to calculate a specific heat we require only 1 gram of copper. So here also we will take 1 gram of copper. Here also if I heat it will to raise the 1 degree Celsius. Here also we will require the same amount of heat, that the specific heat will remain same. Even the quantity is different, but the specific heat of that substance is same, because specific heat here in both the cases what 0.39 joule per gram degree Celsius. Since it does not depend upon the matter, that is amount of matter, you can say that specific heat is also an intensive property.
Thermodynamics equilibrium topic. Consider a gas enclosed in a cylinder fitted with a movable piston shown in animation. The gas has temperature T1, pressure P1, and volume V1. These state functions continue to be constant as long as piston is motionless, and no heat exchange takes place. This is an equilibrium state. Now move the piston in upward direction so that the gas expands. It passes through states for which pressure, volume, and temperature are not specified and vary continuously during the movement of the piston. The gas would then be in non-equilibrium state. Stop the movement of the piston. Suppose at this stage the pressure P2 and volume V2 of the gas and the temperature is constant at T1. The state functions are constant since the piston is motionless. Thus the gas is then in another new equilibrium state. Thermodynamics equilibrium. A system is said to be in thermodynamic equilibrium when its state functions temperature, pressure, volume do not vary with time. Consider a gas pressure P1, volume V1, temperature T1 of gas is constant, as piston is motionless. Then state of system is in equilibrium. As the piston is moving, state function pressure, volume, and temperature of system changes continuously. Then state of system is in non-equilibrium state. As the piston stops, state function pressure, volume, and temperature of system again become constant. Then state of system is in new equilibrium state.
Process and its type.
Isothermal process. A process in which the temperature of the system remains constant throughout the transformation is called an isothermal process.
Consider water is heated in open vessel and temperature is noted by using thermometer. And when boiling point is reached, it start boiling at 100 degrees Celsius. In this system, heat is exchanged take place between system water and surrounding, which causes temperature of system remain constant, that is delta T remain constant. Here heat which is supplied is used to convert liquid water to water vapor. Thus total energy of system remain constant. That is change in internal energy remain constant. Therefore delta U is equal to 0.
Hi, I am Aklesh sir. Today topic: isobaric process. Isobaric process. In isobaric process, the pressure remains constant during the transformation. Here you can see even volume had increased from V1 to V2. Outside pressure, that is atmospheric pressure, applied on piston is constant. So such process where pressure remain constant is known as isobaric process. In the laboratory, chemical reactions are carried out in open containers at constant atmospheric pressure delta P equals 0. I am boiling water and outside atmospheric pressure is constant, that is 1 atm. Can you tell me which process I am doing? Yes, you are right, it is isobaric process.
Isochoric process. It is a process during which volume of the system remains constant. During the transformation, I am preparing food by using pressure cooker. I had closed lid so volume is kept constant. And in this process I am supplying heat, so temperature inside the pressure cooker is increasing, delta T is not equal to 0. And pressure inside the pressure cooker is also increasing, so delta P is not equal to 0. Only volume is constant, so delta V is equal to 0. Since I am preparing food by keeping volume constant, my process of preparing food is isochoric process. Isochoric process. A chemical reaction which carried out in a closed container, that is by keeping volume constant during reaction, is a isochoric. For isochoric process delta V equals 0, that is no change in volume.
Adiabatic process. A process in which there is no exchange of heat between system and the surrounding. So in right side you can see the image. This is a system where I am doing certain thermodynamic reaction. So this is a system, and I am doing all the reaction in the system, but I am not supplying the heat to the system, nor from the system no heat is going out. Matlab there is no exchange of heat take place between system and the surrounding. If such process, such type of system is known as adiabatic process. So what is the definition? A process in which there is no exchange of heat between system and the surrounding. Next, in adiabatic process, the system is completely insulated from the surrounding. So if you can see the image here, this is a insulated from the surrounding. So this is a insulator which is insulated from the surrounding. From there, if there is any heat inside, it will not go outside, and if from outside the heat will not go inside. So this is a perfectly insulated. So I am making one system which is insulated. Now what I will do is I will do a exothermic reaction. You know that what is exothermic? Exothermic is what? Is that reaction where the heat is given out. So in the beaker I will do certain reaction, and in that reaction the heat is given out, but that beaker I have kept inside the insulation. Okay, so whatever the heat will given out, it is trapped inside, it will not go outside. Okay, so and as the reaction goes on, the temperature goes on increasing. Okay, so because there is an increase in the temperature, the internal energy is represented by delta U. That is the amount of total energy of that system will increase. Okay, that is delta U will be increase. Okay, so that delta U is known as what? Internal energy. Change in internal energy, okay, is increase. Next, say another type of reaction we will going to do is endothermic process. Endothermic process means where the heat is absorbed. So same insulation I will take here. Inside a beaker there will be a certain reaction going on, and in this reaction the heat will going to absorb. Okay, so system will use its own energy, it will absorb to do the reaction, and because of that temperature of that system will decrease. So it will going to absorb, the energy is consumed from inside. Because of that, inside the system the temperature decreases. Okay, and because of that the internal energy will decrease. That is the total amount of energy present in the system will decrease. So in both the process, neither the heat is given out of the system, neither the heat taken from the surrounding. So both the process is a adiabatic process. Here Q is equal to 0 is written. What is the meaning of this? Q means what? Amount of heat. Q means what? Amount of heat going into system or going outside from the system. Both is not happening, therefore Q value is 0. Reversible process. Consider a gas which is enclosed in a cylinder and it is fitted with a movable piston. And this piston is very frictionless piston. It is moving without any friction, so it can be easily compressed and expand. Okay, so now the external pressure, which is due to the weight which is applied on the outer side, and that pressure is equal to the pressure of a gas. So since the external pressure and the pressure of the gas is equal, there is neither an expansion take place, neither the compression will take place. Okay, so next, so because of this, the system is in which state? It is in the mechanical equilibrium state. What is the meaning of mechanical equilibrium? Where if the piston is not moving, neither it is expanding nor it is compressing, then you can say that the system is in mechanical equilibrium state with the surrounding. Next, so this is the same diagram which I have drawn here. Okay, now what we will going to do, we will remove certain weight from the outer part. Okay, when we remove the weight, so P external, so this I have removed the small amount of weight I have removed, the external pressure will decrease certain. Okay, that pressure external, it is decreased by a very small amount, so I can assume that dP. Here I have written dP. dP means small decrease in the pressure, because the weight is removed, the pressure is decreased, and because of that what will happen, the piston will move upward because the pressure inside will increase. Because your outside pressure decreases, then the inside pressure of the gas will increase, and the gas and the piston will going to expand. Okay, now if suppose if I add the weight again, see here again I will show you this, I am adding the weight again, what will happen, this process can be reversed. Okay, so this piston will going to move downward. So by increasing the weight again, you can reverse the process and you can bring back to its initial state. Okay, so piston is moving inward. Okay, so the compression will take place by adding the weight again. Now for a mechanical equilibrium, the surrounding infinitesimally with its surrounding, the infinitesimally change may cause the process of occur to be in a reverse direction.
Reversible process. When the gas is in mechanical equilibrium, driving force is equal to opposing force. Here no compression or expansion take place. Now we will decrease pressure by removing weight. So definition of reversible process is any process conducted in such a manner that at every stage the driving force is only infinitesimally greater than the opposing force. There is slight expansion take place, and the process can be reversed by a slight increase in the opposing force is called reversible process.
Features of reversible process. Consider this gas enclosed in a cylinder fitted with a movable piston. Here this gas is in mechanical equilibrium state. What is the meaning of mechanical equilibrium state? Here the driving force and opposing force both are equal. So there will be neither compression, neither expansion. Now if I increase the driving force, so how to increase the driving force? So what we will going to do here, driving force I have to increase. So I have to decrease the force, the outside side. Okay, so to decrease that we will remove the weight. Now the driving force will be more, so there will be a slightly expansion take place. Okay, this is clear. Okay, now again we will increase the driving force. So how to increase the driving force? So this driving force I have to increase. To increase this, again what we have to do is we have to decrease the opposing force. And how to decrease that opposing force? Just remove the weight. If I remove the weight, the driving force will be more and opposing force will be less. Again there will be a further expansion. So this step goes on. Okay, so what is the first step? What is the first feature of reversible process? The driving force and the opposing force differ by infinitesimally small. So here you can see the driving force and the opposing force, the difference is very small. Okay, here also same thing, driving force and opposing force, the difference is very small. Next, this process can be reversed. This process can be reversed by infinitesimally change in the condition. So if I want to bring back to this position from this to this, see how to do. So what we will going to do in this case, same diagram now. Okay, now what we will going to do, we will add a weight. Okay, we will add the weight here. Okay, So as soon as we add the weight, opposing force will be more. Now as compared to driving force, what will happen? There will be a slightly compression. In this way, by putting the weight again, you can bring back to its original position from this state. Okay. So but just by changing the infinitesimally small change makes the process reversed. Okay, next. This reversible process proceed infinitesimally small. This step from one's steps is very small. So first from volume V1 it take place in what? Infinite number of steps. Okay. So to reach from initial volume V1 to final volume V2, this process is very slow. From first step, second step. Okay. So to reversible process proceeds infinitely slowly, and it take place in infinite number of steps. So you can see this reverse process is a very slow process and take place in many steps. So here you can see by slightly removing the weight, you can make number of steps. If I remove again one weight, again there is a expansion. If I remove one more weight, there will be expansion. So to reach from initial volume V1 to final volume V2. So to reach from volume V1 to V2, you are going with many steps. Okay. So reversible process proceed first slowly. This to reach from V1 to V2, the steps is very slow. Okay. Why it is slow? Because there is a many steps in between V1 to V2 to reach from V1 to V2. Then it take place in number of steps. Okay, there is a many steps to reach from initial volume to final volume. Okay, next. At the end of every step of the process, system attain a mechanical equilibrium with the surrounding. So as suppose this is the first step. When there is a slightly expansion, it will get stopped. Now it will attain a mechanical equilibrium state. Now there will be no compression and expansion. So this attained a mechanical at every end of the step. So just like here, step 2 is end after a slightly expansion from here to here. So it attained a mechanical equilibrium state now. So at every steps, the system attained a mechanical equilibrium state with the surrounding.
Irreversible process. In this process, driving force is much more greater than the opposing forces. Consider gas enclosed in a cylinder fitted with piston, and certain weight is added on piston. Let initial volume is V1. Now as all weight is removed, driving force much greater than opposing force. Now the volume V1 increased directly to volume V2 and such type of process is an irreversible process.
Thermodynamic sign convention.
Thermodynamic sign convention. 1. For heat Q. A. If heat is absorbed by the system from surrounding, then Q is positive. Consider system and surrounding. Here heat is absorbed by the system from surrounding. Thus Q is positive. B. If heat is evolved by the system to surrounding, then Q is negative. When heat is released by the system to surrounding, thus Q is negative. 2. For internal energy. A. If there is increase in internal energy of the system, energy absorbed by system, then delta U is positive. If heat is supplied to system, there is increase in internal energy. Delta U is positive. B. If there is decrease in internal energy of the system, energy released by system, then delta U is negative. If heat is not supplied to system, there is decrease in internal energy. Delta U is negative. Work. A. If work is done on the system by surrounding, that is compression of an ideal gas, then work done is positive. Here gas is compressed by surrounding on system. Then compression of gas take place. Then work is done on system by surrounding. Therefore work done on system is positive. B. If work is done by the system on surrounding, i.e. expansion of an ideal gas, then work is negative. Here gases expand, and work is done by system on surrounding. Therefore work done by system is negative.
Derivation of work done in isothermal irreversible process.
Q. Derive an expression for the work done in an irreversible process. 1. Consider a certain amount of gas at constant pressure P is enclosed in a cylinder fitted with frictionless, rigid movable piston of area A. 2. Let volume of the gas be V1 at temperature T.
The pressure exerted by the gas. So this gas is applying a certain pressure, the force. Okay. So that force formula is what? Force is equal to pressure applied by the gas. Pressure applied by the gas against a piston. The piston is moving in the piston pressure is in downward direction and the gas is exerting a pressure in the upward direction. So against a piston into area of the piston, So pressure of a gas into area of the piston is equal to what? Force exerted by the gas. Next, pressure of the gas is denoted by P and the area of the piston is denoted by area A. Okay. Here the pressure of the gas, so this is the pressure of the gas, is equal in what? Magnitude. So for the pressure of the gas, you can see here the pressure, external pressure is in the downward direction and the pressure of the gas is in the upward direction. Both are exerting in opposite direction. So P is equal to minus P external. So instead of P, we will going to write what? P external here. Okay, into area. Okay. So what is the formula of pressure exerted by the gas? Is equal to F equal to minus P external into area. This is equation number 1. Okay, next further.
4. Due to expansion the piston moves upward by a distance d. Let V2 be final volume. Thus change in volume is delta V.
So we have to calculate the work done in an expansion of a gas. So you know that here you can see here that the gas has expanded from the volume V1 to V2 and it covered a distance of d. So we have to calculate how much gas has done the work to increase the volume from V1 to V2. So formula is what? Work formula, you know that in physics we have studied. Work formula is what? Force into displacement. So work symbol is W equal to F into D. In previous slide we have calculated the force formula. Force formula means we have calculated the F and the F value was minus P external into A from equation 1. So we can substitute that F value here. So here it will be minus P external into A into D. Now here A into D is equal to change in volume. How? See here. Here you know that here there was piston initially the piston was at this point, this position. Okay, so if this is the piston which was at the initial position, Okay, I bring here. Okay, this is the initial position, and the piston has moved to certain distance and it has covered a certain distance. Okay, so initial volume was V1 and the final volume was V2. Okay, so the distance covered by the piston is D. Okay, the whole part is look like a cylinder. Okay, so you can say that area into the height, you know that area into height is volume. So area, if you multiply area with what height, you will get what volume of that cylinder. So is A into D, you can write what change in volume. There is a change in volume, so you can say that A into D is a volume change, that is delta V. So A into D you can write delta V. So here A into D, here what will be the formula then? Work equal to minus P external into delta V, and this is the formula for work done in an isothermal irreversible process.
Work done in vacuum. That is free expansion of gas.
What will happen if the gas expand in vacuum? So see here, expansion of a gas against a zero opposing force is called as what? Free expansion. What is the meaning of this? So consider this gas molecule, and now it has a certain barrier. So initially the volume was V1. Okay, when the barrier was there. Okay, now in vacuum what I will do, the external pressure is zero. In vacuum the external pressure is zero, means there is no barrier. So no barrier means I will remove the barrier, and now what will happen? The gas will going to expand, and it will cover a certain distance, and it will go on expanding, and suppose it reached at volume V2. So here the gas is expanding again, and the surrounding pressure is zero. There is no force opposing the gas, and gas is kept on expanding. So this part is the change in volume. So since the P external is zero, so you remember this much, that if in vacuum always the external pressure, in vacuum external pressure is zero. So external pressure is zero, then we know the formula, we have derived this formula, W is equal to minus P external into delta V. So instead of P external you will write 0 there. So 0 into delta V. So what is the answer? 0. So you can say that 0 work is done when the gas expand in vacuum.
Concept of maximum work.
When can we say that the system has done the maximum work? So see, first we will consider the free expansion. You know that in a free expansion, in vacuum, in free expansion means in vacuum, the opposing force is zero, that is P external is zero, there is no barrier, means gas expands. Okay, and in this type of expansion, the work done, if I calculate, the work done is minus P external to delta V, and since the external pressure is zero, the work done is zero. So we can say that in vacuum when the gas expands, the work done in changing the volume is zero. There is no work done by the system. In reversible expansion, so consider this is a gas which is fitted with a piston and a weight is added. So there is a certain opposing force, and it has a volume V1. So in irreversible expansion, opposing force is less than the what? Driving force. So to decrease the force, we will remove this weight. Okay, so I am removing the weight, and because of that P external weight is less, and because of that internal pressure increases. So and it get expand. Okay, so expansion take place. Okay, when the P external is very less as compared to driving force, or you can say like that also, driving force is much greater than the opposing force. If such a condition is there, the gas will going to expand, and in such a situation there is some work is done by the system. So to change the volume from V1 to V2, there some work is done. Next case, Next is reversible expansion. For reversible expansion, opposing force must be infinitesimally smaller than this opposing force. This is the opposing force. Its force should be very small as compared to what? Driving force. Okay. So if such a situation is there, then the maximum work will be done by the system. Okay. So if the let us assume that pressure of the gas is P and it is differ from P external. So this gas pressure is slightly more than the opposing force. So to increase the pressure, we will remove certain weight from here. Very small weight is removed from here. Okay. So that is denoted by dP. So I am removing certain weight, means I am removing certain pressure is decreased. Opposing force, that is P external, small part pressure is decreased. Because of that, the gas will expand slightly. Okay. So here dP is what? So you can say here P minus P external. So this is more than this. So P minus P external is equal to what? Change in pressure. So that dP is what? Change in the pressure. So because of that, the P external is equal to what? P minus dP. Therefore work is equal to minus, formula is what? W is equal to minus P external into delta V. So P, instead of P external, you can write there minus P external to delta V. So instead of P external, you can write P minus dP. So what is the formula? W is equal to minus P minus bracket P minus dP into delta V. And here the work is done, but very small work is done, where there is a slight expansion take place. So this is the work done by the system. If the pressure removed is very small, then the work done is also very small. Okay. And here you can say that the maximum work is done by the system. Okay. And always remember that maximum work is done by the thermodynamic reversible process. If the system is in reversible expansion, then the system will do a maximum work. Derivation of maximum work done by a system in an isothermal reversible process. So derivation question is, derive an expression for maximum work done. Consider a n mole of an ideal gas enclosed in a cylinder. So this is the n mole of gas which is enclosed in a cylinder. This is a cylinder and is fitted with a frictionless movable piston. So this is the piston which is very frictionless. It can expand and contract very easily without any friction. It expands isothermally and reversible for the initial volume V1. So there is the initial volume of the gas was V1 and it will going to expand isothermally and reversibly. Means it will expand very slowly. To final volume V2. Suppose we assume that this part that is this dotted one is the final volume. Okay, so to reach this final volume, this will expand very slowly it will go and then it will reach to V2. So here at temperature T, so the temperature of the gas or outside temperature is constant, that temperature will not change. That's why it is what? Isothermal. Isothermal means temperature will remain constant here. So expansion take place in number of steps. To reach the volume from V1 to V2, it will take many steps. 1, 2, 3, many, you don't know how many steps. Many steps will be taken depending upon how the weight is removed. It will expand very slowly to reach the final volume V2. During each step, the external pressure, that is P external, that is opposing force, is made infinitesimally smaller than the pressure of the gas. This is the pressure of the gas. So what we will going to do here, the external pressure will decrease the pressure slightly by removing the weight. So by removing the weight, to decrease the pressure outside, we will gradually remove the mass from the piston. So I am removing the mass from the piston. Now what will happen? P external pressure will decrease slightly and P pressure will increase slightly. Because of the increase in pressure, this piston will going to move up. Okay, slightly it will going to expand because the weight is very small, the pressure decrease is very small, the expansion will be very small. So this process will go on repeating. Next case, suppose it has now again if I remove the one weight again, so then there will be a slightly expansion will take place. Okay, again there will be expansion. Okay, suppose again if I remove the weight, again there will be a slightly expansion. So is in that way many steps will be taken place to reach the final volume V2. So until the V2 volume is attained, okay, this process goes on. Okay, final volume. Now when the volume of the gas increased by infinitesimally small, so you know that the last part here, the dotted one here, initially this piston was at this position, now it has increased to this position. There was a small increase in the volume, change in the volume, or you can say increase in the volume in that single step. In that, very small quantity of work is done. So dW is the work done in expanding very small volume, that is dV. The work done is very small, that is dW. So dW formula, work is what? External pressure into dV minus P external into delta V. This formula we already derived in the last slide. Okay, so see dW is equal to minus P external into dV. Next, as the expansion is reversible, so if you want to reverse that reverse means whatever the expand was there, again if you want to bring back into the initial position, again we have to add a small weight. If you add a weight, then what happen? Then the external pressure will increase slightly and it will get compressed slightly. So here the compression will take place. So this is the case. If P is greater, for reversibilization, if P is greater by very small quantity, that is dP, then P external. So if I decrease the external pressure by dP, so what will happen? The P will increase slightly by dP. So that is written here. So P will increase by what? dP, because dP you have removed from the outside. So P is greater by what? Small dP from the external pressure P external. Okay. So there is a slightly expansion will take place. Okay. So in this case P is greater than P external, and how much greater? dP greater. So P minus P minus P external is equal to difference is what? dP, and dP is called as what? Infinitesimally change in the pressure. So just shifting this P external is negative, I will bring on the right hand side, dP on the left hand side. dP will be negative and P external will be positive. So P external positive is there, P minus dP. Okay, so this is equation 2. Now from equation 1, you know that we have derived the formula dW is equal to minus P external into dV. So here the small work is done. So this dW here you can see, by expanding that volume, that is small volume dV, small work is done by that system. So small amount of work done by the system is equal to what? P external into dV. That is the formula. Therefore dW is equal to from equation 2 it is equation 2 is what? P external equal to P minus dP. So instead of P external we will write here P minus dP. Already minus is there, just we have to write, instead of P external we have to write P minus dP into dV. Now we will open the bracket, so minus will go inside and dV also go inside. So minus P dV, so minus P dV, then minus dP into dV, in multiplication of this, so dP into dV, and minus into minus plus dP into dP. Okay, dP into dV, neglecting the product dP into dV, since here already the dP is very small, dV is very small, and multiplication is still very small, so we can neglect this dP into dV in the next step. So formula will be next dW equal to minus PdV, and this part will be become 0. We are neglecting it. Okay. Now this is the equation 3. Now total work done during the entire expansion from V1 to V2. So this gas was initially at V1 and it go on increasing as the weight is removed. So the small work is done and small volume will be increased, and finally it will reach to the final volume V2. So you can say that to reach from volume V1 to final volume V2, you have to do many steps. It will go in many steps. Okay, there is a very small increase. So total work, if you want to find it, we have to integrate this equation 3. Total work done obtained by integrating equation 3 between the limit initial and final state. What is the initial state? Volume V1. What is the final state? Volume V2. So for to reach the gas from volume V1 to volume V2, total work done, if we want to calculate, we will integrate this. That is the sum of all the work done, small whatever the work was done to reach the V2, that all total work we will going to add. So instead of addition, we are doing integration. Integration means sum of all. Okay, so dW minus PdV. Now we will integrate from initial to final. And what is the meaning of this? When we write integration and initial and final, it means we are doing the total, we are finding the total work done for the system to reach from initial state to final state, that is from V1 to V2. Okay, total how much work the system has done, integrating on both the side. Here initial here the dV is there, what is the change in the volume? So the initial volume was V1 and the final volume was V2. Okay, next step. So this we have done till here. Now using the ideal gas equation, what is the ideal gas equation? PV is equal to nRT. Therefore P equal to what, this V part will be bring down. So P equal to nRT upon V. So instead of P here, we will going to write here nRT V. Okay, so next step will be, this is the total work we are going to find out maximum work done by the, you know that this is a isothermal reversible process, so work done will be maximum, therefore the symbol will be W max, maximum work done, is equal to minus instead of P we will write nRTV, so minus nRT upon V and this dV. Okay, since here the temperature is constant, R is universal gas constant, and in this process number of moles of gas has not changed, only the volume is increasing, but the number of moles of gas which is present in the cylinder is constant. So bring this nRT outside the integration because it is constant. In integration, whatever the constant there we are bringing outside the integration, so remaining part is what, 1 by V dV. Now nRT is there, integration of 1 by V dV is log V, exponential log V. So exponential log V, and in this integration limits 1, we have to make a bracket. Okay, make a bracket, and there you write V1 and V2. Okay, so formula is what, log to the base E V, yeah, or you can say exponential log V, and V1 you have brought here and V2 brought here. This is the limit part. Now next step, what we will do, minus nRT, and this is a bracket. This V2 will go here, instead of V we will write here V2. See, V2 is going inside, so here you will write here ln V2, then minus, then V1 will go inside instead of V, so here it will be what, log to the base E V1, log to the base E1 V1. Okay, then nRT, instead of minus you will write divide, V2 upon V1. Okay, so here it is a log to the base E. So to make it log to the base 10, here outside n, or you can say outside the log, you will write number 2.303. So log to the base 10 V2 upon V1, and outside you will write minus 2.303 nRT. Okay, so whenever you bring the log exponential log into log to the base 10, in the front you write 2.303, so equal to minus 2.303 nRT log to the base 10 V2 upon V1, and this is the maximum work done by the system. This is equation 4. Now according to the Boyle's law formula is what? At Boyle's law, temperature is constant. So whenever the temperature is constant, formula is what? P1 V1 equal to P2 V2. So arranging this, so V2 is there, V1 will go downward and P2 will go down. So this is the format. So already we have got V2 upon V1. So instead of V2 upon V1, we can write P1 upon P2. So just write the same part, only instead of V2 upon V1, we will write P1 upon P2. So W max equal to 2.303 nRT log to the base 10 will be same, and instead of the V2 upon V1, we will write here P1 upon P2, and this is the equation 5th. So equation 4 and equation 5 is the maximum work done in an isothermal reversible process. Work done in a chemical reaction. Work done in a chemical reaction derivation. So this is a piston which is expanding, okay, and it increased from volume V1 to V2, and the external pressure is constant. So work done by the system at constant temperature and pressure. So by keeping the temperature constant and external pressure constant, okay, so what is the work done by the system? So you know the formula, work is equal to minus P external to delta V. If you know the change in the volume and what is the external pressure applied by the surrounding, you can calculate the work done by the system. Since the reaction occur at constant external pressure, here the external pressure you are not changing, you are keeping constant, okay, the P external will be equal to P. So instead of P external, we can write there P. P external we can write there P. So minus P, what is the change in volume? Change in the volume is equal to final minus initial. Final volume is V2 and initial volume is V1. So V2 minus V1. So here in delta V, we will write here P, V2 minus V1. Now opening the bracket, we will open the bracket to minus P into V2, minus into minus plus V, PV1. So minus P into V2, then minus plus, then minus plus, then P into V1. Okay, this is equation 1. Then according to the ideal gas equation, formula is what? PV equal to nRT. So PV1 equal to N1RT, PV2 equal to N2RT. Here pressure and temperature is constant, R is universal gas constant, so there is no 1 and 2 here. Only the volume is changing and the number of moles can be changed, because in the reaction number of moles can increase or number of moles can decrease. So W is equal to, say here instead of PV2 we can write N2RT. So PV2 instead of PV2 N2RT plus instead of PV1 N1RT. So here we will write N1RT. Okay, at constant temperature and pressure, then what is common here? Minus, if I bring outside, so here minus plus, okay, minus also go out and RT will go out. So what is the remaining here? RT will go out from both the side and minus will go from outside. So remaining value N2 minus N1. Okay, so the difference in the number of moles is delta Ng. Okay, and delta, this is the above reaction where the work done by the system in a chemical reaction. So what is delta N? Delta N is the difference in the number of moles of gaseous product minus number of moles of gaseous reactant, and 1 is the number of moles of gaseous reactant and 2 is the number of moles of gaseous product. Okay, next case 1. Suppose N2 is greater than N1, that is number of moles of product is greater than number of moles of reactant. Reactant is less, product is more. Then delta Ng is greater than 0. So here you can say, suppose A is a reactant reacting and giving a product, and the product number of moles is greater. So number of the moles of, that is N2 is greater than N1. N2 means number of moles of gaseous product is greater than the number of moles of gaseous reactant. So in this case, this will going to expand because the volume is increasing, number of moles is increasing. As the reaction goes on, number of moles of product is increasing. So the gas will going to expand. So the work is done by the system. So work is done by the system. The work formula is W is equal to minus delta N G RT, already derived here. Since here delta N is greater than 0, delta N is greater than 0 means what? It is positive. If it is positive, positive and negative is negative. That means the work will be negative. Work is negative means it is less than 0. And if the work is less than 0, work is done by the system. Next, case 2. Just opposite of case 1. N2 is less than N1. Okay, suppose here see 2A gives B, means what? Reactant is more, product is less. My volume is decreased, number of moles has decreased. So number of moles decreases means what? N2 minus N1. So here will be less than 0. See, N2 is more and N1 is, sorry, N2 is less and N1 is more. So less minus greater, answer will be negative. Therefore delta N is less than 0. That is, it is negative. This is negative and negative. Formula negative and delta N is negative. Negative, negative, positive. So work done is greater than 0 means work done is positive. So work is done by the work is done on the system. Okay, so you can see here in the animation also. So here is work is done on the system because the volume has decreased. So work is done on the system. In case 3, what will happen? If the number of moles of reactant and product are same, means what? During the reaction A gives B, there is number of moles are same. The delta N G, there is no difference, 0. So work will be 0. And if work is 0, no PV work is done, means no work is done by the system. And when will happen this? When the number of moles of reactant and products are equal.
Units of energy and work. Now let us understand the units of energy and work. First, the SI unit of work is joule. 1 joule is equal to 1 kilogram meter square per second square. Now, work is force multiplied by displacement. Force is equal to mass multiplied by acceleration. So we multiply kilogram meter per second square by meter. When we multiply meter by meter, we get meter square. So finally, the unit becomes kilogram meter square per second square. Therefore, 1 joule is equal to 1 kilogram meter square per second square. It can also be written as 1 joule is equal to 1 Pascal meter cube. Now, work is force multiplied by displacement. Force is equal to pressure multiplied by area. Therefore work equals P multiple by R multiplied by displacement. So work is joule, which is equal to Pascal multiple by meter square multiplied by meter. There 1 joule i.e. equal to Pascal meter cube. Now, the work formula. Work is equal to minus P external into delta V. If pressure is expressed in bar and volume is expressed in decimeter cube, then the unit of work becomes bar decimeter cube. Now let us see the conversion. 1 bar is equal to 10 to the power 5 Pascal. 1 decimeter cube is equal to 10 to the power minus 3 meter cube. Therefore, 1 decimeter cube bar is equal to 10 to the power minus 3 meter cube multiplied by 10 to the power 5 Pascal. When we multiply these values, we get 10 to the power 2. 10 to the power 2 equals 100. So finally, 1 decimeter cube bar is equal to 100 joule.